This video assumes you've completed the GS20 basic configuration video, this guy, can control the spindle locally from the drive's keypad, and have a switch configured to enable the CNC to control the drive. You'll also need an AltMill CNC machine that's built and can jog to various axes, and you're now ready to configure it and the drive so the AltMill can control the GS20 drive via PWM, which will then control the spindle. This is a list of everything we'll be doing in this video in the order we'll be doing it. We'll start by configuring the drive, then we'll make sure gSender is set up correctly. We'll be using the default settings, so that's already done. Then we'll test it, where we usually find out that the PWM converter is not set up correctly. So I'll show you a quick and easy way to fix that, and then we'll test it again and verify it. At the end of the video, I'll introduce how to make a drive-ready indicator, how to automate dust collection, how to configure an unsupported custom drive for RS-45, and braking for fast deceleration times. If you're already familiar with how to do all this stuff and just need a list of what to do, take a screenshot of this slide and this schematic. Stop the video and go do it. For everyone else, stick around. I'll walk you through this and share some insights and tips so you can get the most out of your AltMill CNC router with a Durapulse GS20 series drive. Here we go. The drive and CNC should both be on and ready to go. And don't forget to reset the e-stop on the AltMill. Go ahead and switch to CNC control and leave it there for the rest of this video. The AltMill's controller can send out a PWM signal to tell the drive what speed the spindle should be at. But the GS20 drive doesn't have a PWM input. It does have a 0 to 10 volt analog input, so we need to add a little PWM to 10 volt converter board. I use this one from Amazon. You can use any one you want, they're all pretty much the same. Just make sure it has a potentiometer adjustment, it takes a 5 volt 0 to 100% duty cycle PWM in, can handle PWM signals in the 1 to 3 kHz range, and can handle a 24 volt supply voltage. Let's do the wiring first. This is the stuff we'll be doing in this video. Everything else was covered in that basic configuration video. On the AltMill's SLB EXT controller, in the upper left corner, the PWM signal comes out of this green connector. Wire that in the ground to the PWM converter board. The board I'm using is labeled on the back. Then take the 0 to 10 volt DC output signal and then connect it to the analog input 1 terminal on the drive. That would be here on the drive's terminal strip. I love that the GS20 series drives always have a handy terminal strip layout chart like this one inside the drive's cover. The PWM board needs a 12 to 30 volt power supply, and fortunately, the GS20 just happens to have that right here. So we wire the 24 volt reference voltage on the drive to the voltage input on the PWM board. That's here on the GS20 drive's terminal strip. Now the GS24 volt terminal is capable of generating 100 milliamps, which is exactly what the PWM converter board says it requires. I assume that's for the 12 volt end of things, so since we're supplying 24 volts, it's probably only using half of that current. Which is good, because we'll want to use that 24 volts to drive other things like the automatic dust collection and indicator lights. If you run out of current, well, just add an external 12 to 30 volt supply in place of the drive's 24 volt reference. Okay, we just finished this part of the schematic. Now I do want to point out that this little PWM converter board connects all of these grounds, which means our analog and digital grounds are now coupled. I wish they had isolated the analog output, but we'll be able to filter the analog input to the drive using parameter 3.15 if we need it. And I've never had to, so I think we're okay. On a GS20 drive, there's a space for option modules here. So I use this screw hole to mount the PWM board. It fits perfectly and rests up against this protrusion here, so we're good to go. Okay, let's set up the drive parameters. Let's configure the analog input to the drive. The user manual tells us parameter 0.20 is where we tell the drive to use an analog input to control the drive's frequency when in remote mode by setting this to a 2. On the drive, we hit the Enter key to select parameter group 0, Enter to accept, and 20 to select the parameter number. Enter to accept, then enter a 2 to tell the drive we want to use the analog input to control the frequency or speed of the spindle. Setting parameter 3.0 to a 1 tells the drive to use analog input 1 for that frequency control. We could use analog input 2, but it can handle both voltage and 0 to 20 or 4 to 20 milliamp current loops, so I like to save that one in case I need the flexibility later. Parameter 3.15 controls the filter time for analog input 1. We'll leave it at the default, just know that you have this available if you need to smooth out your 0 to 10 volt signal. Just don't go crazy with it, it'll slow down the response time of your system. So we only needed a couple parameters to get the analog input working. Cool. If we set parameter 2.0 to a 2, then digital input 1 becomes the run stop control, and digital input 2 becomes the reverse forward control. Now by convention, the thing you state first is the active low signal. So in this case, run and reverse are logic low signals, which is exactly what the AltMill control outputs, so we're not going to have to worry about inverting those signals. Inputs are pulled up by the GS20 drive, and the AltMill controller has active low outputs, so this works great. On the AltMill controller, we just run wires from these screw terminals along with the digital common, that connector looks like this, and then plug the run stop wire in here, the reverse and forward wire in here, and the digital common here. That's these guys on that handy chart that you'll find inside the drive's front cover. If you need to remove a wire, just press the button next to it and pull. I use these ferrules to make inserting wires super easy. Just shove them in. These clamping connectors are another feature I really like about the GS20 drives. Well, that's all we need to get the drive to accept analog input to control the spindle speed, run stop, and rotation direction. One more thing. We're going to need to see the analog voltage coming into the drive for our testing. The GS20 has a user configurable display field on the keypad that you can use to show a ton of different things. If we set parameter 0.4 to an 11, it'll display a 1 reminding us that we're looking at analog input 1, and it'll show the analog input as a percentage of the full 0 to 10 volt range. We'll use that in just a minute. Now let's go over to gSender and connect to the AltMill. I'm using gSender 1.5.7 for this video. Great. Go to Config, Spindle Laser. I'll enable this guy and apply it so we can control the spindle from the main carving screen. These should all be in their default settings as shown here. If any of these are highlighted in yellow, like this guy, then they've been changed from the default. The main thing is make sure the generic SLB drive is selected. That automatically sends out PWM speed control pulses. Now this is important. If you changed from something else like RS-45 control to this PWM control, then you need to hit apply and then power cycle the AltMill and do the e-stop reset thingy. If you're already in PWM mode, then you can usually skip the power cycle step if you want to. We're done. Let's go back to the main screen, and down here we'll bring up the Spindle Control tab that we enabled a minute ago. If we try to run a spindle, nothing happens. If we increase the speed, there it is. If we go to the max speed and bring up the tachometer, we see we're basically at the spindle's max speed, 24,000 RPM. So that's good. What's going on down here? We're telling it to go at 7,500 RPM, right? Well, here's the trick. These labels don't do anything in PWM mode. They're just labels. We need to adjust the PWM so it matches these labels to make these labels mean anything. So we'll need to specify a minimum PWM that gives us 7,500 RPM and a max PWM that gives us 24,000 RPM. Make sure this spindle speed slider is all the way down to the minimum position, then go back to Config, Spindle Laser, and scroll down to PWM. And look, there they are, min and max PWM. I'm going to take a bunch of measurements and plot them so you can see what's going on. You don't need to do this. I'm just doing this so you can visualize what's happening. Then, once we see what's going on, I'll show you how to skip all this. So bear with me while I'm walking you through what I'm doing. I'll start the minimum PWM at 10%, and then scroll up here to enable the spindle. On the drive's keypad, I'll hit the menu button a couple times until I see the analog input user display that we set up earlier. It says it's analog input 1, and the voltage is this percentage of the 0 to 10 volt scale that the drive is seeing right now. I'll make a note of that analog value. Stop the spindle, scroll back down to min PWM, and bump it to 20%. Scroll up and enable the spindle. Note what the display says the analog input is. Stop the spindle, scroll back down to PWM, and set the min to 30%. Scroll back up and enable the spindle and record that value. You get the idea. I repeated that in 10% increments all the way to 100%. Plot that, and we get this PWM versus analog voltage chart where the voltage is in percentage of full scale. Well, that doesn't look very good. It's not real linear, and it saturates around 80% PWM. Clearly, the gain on that little PWM converter board needs to be adjusted down. To do that, just select a midpoint like 50% as the min PWM and adjust the potentiometer on the converter board until we see the analog input on the drive's display roughly at 50%. Let's do that. Set the min PWM to 50%, apply it, and enable the spindle. Adjust the potentiometer on the PWM converter board until the drive's display says the analog voltage is near 50%. I'm using the GS20's virtual keypad that comes with the free GS20 Drive configuration software because it's easier for you to see and for me to record while I adjust the PWM converter inside the drive. I then went back and recollected the PWM samples over the entire range again. This time I got a curve like this. Much better, nice and straight, but still goes non-linear near the top end and never gets to 100%. Now this is pretty typical for these PWM converter boards. So to ensure a linear response over the entire spindle speed range, I've gotten in the habit of just using a 90% PWM as my top end. That avoids these kinds of issues, which means we need to raise the curve until 90% PWM gives us a 100% analog input. To do that, I set the min PWM at 90%, apply, and enable the spindle. Adjust the potentiometer on the PWM converter board until I just get 10 volts out, or 100% on the drive's display. I then resample the full PWM range again, and now our plot looks like this. Look how linear it is, a nice straight line. And a 90% PWM now generates the max RPM, which for us is 24,000 RPM. So we enter that into the gSender configuration right here as the max PWM. Now we need to figure out which min PWM value will give us 7,500 RPM, which on our graph is 31.25% of 24,000 RPM. Now you could do this by trying different min PWM values until you hit 75 RPM, but it's a lot quicker to just calculate it using some high school algebra that says, given 2 points on a line, you can find a third. We'll use the 90% and 20% PWM values to calculate the one we want. These are the 2 points on the line we'll use from that graph. We want to find the PWM for 31.25%, which is where 7,500 RPM is on the 24,000 RPM scale. Step 1, find the slope of the line. Put our values in, and we get this. Step 2, given the point slope equation of a line, we put in our slope, one of the points, and the desired RPM in percent, and solve for the PWM value that will give us 7,500 RPM. Enter that here as the minimum PWM, and accept it. Go back to the main screen. With the slider all the way to the min PWM, enable the spindle. And sure enough, we get basically 7,500 RPM. Go to the max value, and yep, we get 24,000 RPM. And you know it's linear from end to end. Perfect. Okay, remember, you don't need to go through any of this. I was just doing it so you could visualize what's going on. All you need to do is set the min PWM to 90% in gSender and adjust the potentiometer to get 10 volts out of the PWM converter board, which will show as 100% on a drive's display. Take one measurement at the low end and plug the results into the above equations. Here's the step-by-step procedure. Now before starting, make sure the spindle slider is all the way to the left. First, adjust the top end. Go to Config, Spindle Laser, scroll down to PWM. Change the min PWM to 90%. Scroll up and enable the spindle. Adjust the converter potentiometer until the analog readout on the drive keypad just touches 100%. These potentiometers can be real touchy, so play with it until you get a solid reading. Usually going past what you want and then coming back to it works well. Stop the spindle. Second, measure a point near the bottom end. Scroll down and change the min PWM to something else. We use 20% in this video. Don't go all the way to 0. It usually isn't linear down there. Start the spindle. Note the analog value on the drive's display. Finally, do the math. Plug the 90 and 20% points into the math to calculate the PWM value we need to get 7500 RPM, or whatever value you used on your min label for the slider control. Put that result into the min PWM and put 90% into the max PWM. And finally, go back to the main screen and try it. A couple notes about setting up PWM. This enables PWM output. I can't think of a time when you would ever want to use this, so just leave it alone. For example, if you decide to use RS-45 to control the drive, it automatically takes control, so even then you don't need to mess with this. You can tell gSender to stop the spindle anytime it gets an S0 command, and to start it anytime it gets a non-zero S value. Now I haven't used that yet, but I suspect it might be useful when doing laser stuff. I am thinking about doing some laser how-to videos in the future. Let me know in the comments if that would be helpful to you. Earlier, we saw that the control signals out of the AltMill controller had the same polarity as what the GS20 drive was expecting. If they didn't have the same polarity, well, we could invert them here. This is the frequency of the PWM signal. The converter we used can handle 1000 to 3000 Hertz, so this is fine. If you get a board that needs something else, well, put that value here. If we bring up the PWM on a scope, sure enough, we see it's operating at 1 kHz. And if I change the spindle speed, we can see the PWM change. Go all the way up, and yep, we get a 90% active PWM signal for our top end. Slow the spindle all the way down, and we get the PWM value we calculated for the min PWM. How about that? Remember when we tried to run the spindle at the minimum value before we adjusted things and we got no spindle rotation? Well, that's because this guy forces the spindle to stop whenever you send it a 0 PWM, or whatever value you put here. I can't think of a reason to change that, so just leave it alone. The minimum value label on the main page slider, this guy, is specified here. You can change it to whatever you want. Just don't forget to use your value in the math instead of the 7500 we used. Now keep in mind, these inexpensive DIY spindles are not designed to operate at low speed. They usually need to stay above 6,000 to 8,000 RPM. Below that, they'll draw a lot more current, get a lot hotter, and will definitely shorten their life and may even eventually burn up. 7500 is a good, safe number to use. If you have a spindle that says it's designed for an RPM lower than 7500, well yeah, go ahead and use it. Finally, you may want to switch parameter 0.4, the drive's user display, back to showing RPMs instead of the analog input by changing it to a 7. That's it, we're done. Check out these videos to learn how to set up the drive ready indicator light so you know when the drive is on, and more importantly, when it's fully discharged and off. How to make your dust collector system automatically come on when the spindle's in use. We'll be using one of the drive's outputs to control that. How to set up an unsupported custom drive for RS-45, and how to add braking to get super fast deceleration times. If you want to try the free configuration and debug software, watch this series of videos. And since this drive has a built-in PLC, there are also videos showing how to program the PLC. And yes, that PLC programming software is also free. Well, that's enough. Go have fun with your CNC.